All right, welcome to the Explainer. Today, we are exploring an invisible scale that chemically rules absolutely everything around us. I'm talking about the rain falling outside your window, the blood pumping through your veins, all of it operates on this hidden numerical code. We're talking, of course, about the pH scale. I am so excited to guide you through this data today because honestly, once you start seeing the world through this 0 to 14 lens, you really begin to realize just how intricately balanced our chemistry really is. So, to get us started, I want you to think about this question. What do battery acid, a lemon, and your very own stomach have in common? I mean, on the surface, a corrosive industrial chemical, a citrus fruit, and a human organ seem completely unrelated, right? But on a chemical level, they actually share a surprisingly similar, incredibly intense environment. As you'll see today, the chemical connections hiding in plain sight in our daily lives are absolutely fascinating.
Okay, let's dive into this. Here is our roadmap for today. 1. Decoding the pH scale. 2. The highly acidic zone. 3. Everyday mild acids. 4. The neutral middle ground. And finally, 5. The basic extremes. Section 1. Decoding the pH scale. The rules of the road. Let's get our bearings before we start mapping things out.
So what does pH actually mean? It stands for the potential of hydrogen. It's simply a quantitative measurement of how acidic or basic an aqueous or water-based solution is. The entire scale is locked between the numbers 0 and 14. But what is that number actually telling us? Well, it indicates the concentration of hydrogen ions floating around in the solution. This one single measurement reveals the hidden chemical potential inside practically all of our everyday items.
You probably remember this from science class, right? To visually distinguish these, we use the classic litmus test. So, here's the golden rule for our journey today. If the pH scale is less than 7, the substance is an acid, and the litmus paper will turn red. If the scale is more than 7, it's a base, and the paper turns blue. Red for acid, blue for base, with 7 sitting right perfectly in the middle. It's a beautifully simple rule to keep in mind for the rest of this explainer.
Section 2. The highly acidic zone. Plunging into the deep end.
We're starting our journey at the absolute lowest, most intense end of the scale. Down at a pH of 1.0, we find battery acid. This is incredibly corrosive stuff. Batteries actually use this acid in a chemical reaction to produce an electric current. Specifically, they use sulfuric acid, which is an intensely strong acid that allows our cars to start and our electronics to function. But here's what's absolutely wild. Right next to that corrosive battery acid, sitting at a pH between 1.0 and 3.5, is our gastric juice. Our own stomachs are incredibly acidic. They use this unique combination of hydrochloric acid, lipase, and pepsin. And why? Because this highly acidic environment's main function is to basically inactivate harmful microorganisms. We literally carry around a vat of acid right next to battery acid on the pH scale just to protect us and digest our food. No way, right? Moving right along to Section 3, Everyday Mild Acids, the edible middle.
What's really surprising about this zone, mostly in the 2.0 to 6.0 range, is that almost everything we love to consume lives right here in the red territory. Look at the stuff we drink every single day. We start our mornings with coffee at a pH of 5.0, or maybe tea at 5.5. Later on, wine sits way down at a surprisingly highly acidic 2.8, and beer at 4.5. And those soft drinks, they are super acidic, ranging from 2.0 to 4.0. We are constantly bathing our mouths and throats in surprisingly acidic beverages. To put that into perspective, just look at the massive pH gap between acidic soft drinks, averaging around a 3.0, and pure drinking water, which sits perfectly neutral at 7.0. It really drives home what we are putting into our bodies. Every single time you sip a soda, you're introducing a chemical environment that is substantially more acidic than the water your body naturally craves.
And it's not just our drinks, it's our food too. Lemon juice is an acidic 2.2 to 2.4. Strawberries and tomato juice also sit quite low on the scale. Now these fruits get their low pH from things like citric acid, ascorbic acid, and malic acid. But notice how dairy behaves. Curd is around 4.5 to 5.5, but fresh milk climbs up to 6.5 to 6.7. So it's still technically a little bit acidic, but it's creeping much closer to that neutral center line. Now you might be wondering, with all this acid we are eating and drinking, how do our teeth not just completely dissolve? Well, the crucial factor here is human saliva.
Ranging from 6.2 to 7.6, the flow of your saliva actively works to clean up the mild acids we just consumed. It actually eliminates carbohydrates that bacteria can metabolize and actively removes the acids produced by those bacteria. It is literally our body's built-in pH balancer.
Which brings us perfectly to Section 4, the neutral middle ground, the Goldilocks zone.
We've finally reached the dead center of the 0 to 14 scale. At exactly pH 7, substances are considered completely neutral. They have neither acid nor base qualities. Pure drinking water sits precisely here. But interestingly, so does common salt. Salt actually contains both a strong acid and a strong base, which basically cancel each other out, meaning it does not get hydrolyzed. It exists in perfect, peaceful balance at exactly 7.0.
But here's a fun fact. As humans, we aren't perfectly neutral. Our blood plasma operates in this incredibly narrow window, 7.35 to 745. We don't operate at a flat 7. We operate in a razor-thin, mildly basic window, just slightly above neutral.
And the precision required here is staggering. It's absolutely crucial. If our blood steps even slightly out of this delicate Goldilocks zone, the medical consequences are severe. If the acidity in the blood increases, dropping the pH down, we enter a dangerous state called acidosis. On the flip side, if the blood becomes too alkaline, rising above that tight window, we experience alkalosis. Our very survival depends on this strict regulation of our internal pH.
Okay, Section 5. The basic extremes. Accelerating to 14, we've officially crossed the neutral line, and we're making our final push up the basic side of the scale.
Just like mild acids absolutely dominate our food, mild bases dominate our cleaning and cooking routines. Soap ranges from 7.5 to 9, utilizing its basic nature to break down grease and grime. Oil can range from 9 to 11, and a staple of almost every single kitchen pantry, baking soda, sits squarely at a basic pH of 9.
But as we climb higher, things escalate fast. We're getting into dangerous territory. Ammonia and bleaching powder sit at a potent pH of 11. By the time we hit a pH of 13, we are looking at sodium hydroxide and the concrete we use to build our cities. Just like those extreme acids down at pH 1, these extreme bases at the high end of the scale are highly reactive and require extreme caution to handle safely.
And this perfectly shows what happens when the opposite extremes of our scale meet. If you take that basic bleaching powder at a pH of 11 and introduce it to an acid like hydrochloric acid, they react aggressively. The reaction produces calcium chloride, chlorine, and water. So you see, the pH scale isn't just some static list of numbers. It's a map of chemical potential, showing us how substances will interact, often violently, when brought together.
Let's zoom out for a second and look at the whole planet. We've seen how our bodies strictly regulate pH, but what about the Earth? Well, acid rain, which has a pH of 5.0 to 5.5, occurs when normal rain combines with sulfur dioxide or nitrogen oxides. These are emissions produced by the burning of power plants and automobiles. So through pollution, human activity is actively lowering the pH of our environment, pushing it further down into the acidic zone.
Which leaves us with a massive question to chew on. We've seen today how our blood, our biology, and our environment rely on an unimaginably delicate chemical balance. We know exactly where the safe zones are on that 0 to 14 scale. So if we know how delicate this all is, how will our continued human activity actively alter the pH of the planet we call home? It's a heavy question, right? But it's definitely one worth keeping in mind next time you see rain falling, or hey, even just squeeze a lemon. Thank you so much for joining me on this explainer. Keep your curiosities high, and I'll see you next time.